Reminder what this means. It means that AI satisfies Q restricted to M and all the previous ones. Oh, I forgot to say, and A0 has the same type, or let's say A0 is A. So starting with A. Okay, so the difference between the usual definition of dividing and Kim dividing is that in the usual definition of dividing, you just say there is some indiscernible sequence such that this family is inconsistent. And here I'm saying that this indiscernible sequence is somehow generic in the sense that it satisfies that it's a Morley sequence of some global invariant type. Okay. So remember last week I said that every such sequence is indiscernible. Okay. So the indiscernibility just follows. Okay.
By the way, this is equivalent to for any. So if there is a
yeah, that's exactly
global,
that's exactly what I'm going to prove now. So just in simple theories, dividing equals that's essentially Kim's lemma, that once you have a formula that divides, then every formula that divides, take any such sequence, it will witness dividing. Okay. So in particular, there exists some. Of course, Kim dividing implies dividing. So just say Kim always implies dividing, because Kim dividing says there exists a special kind of indiscernible sequence, and dividing just says that it's some. Okay, so this is just a remark, but actually in simple theories, because what I said, it's not only that if something divides, then there exists some such sequence, but actually for all such sequences. Okay, so that's exactly the content of the next lemma. So what again? Yeah, but it is a Morley sequence. Once it's like that, once it's a Morley sequence of some invariant type, it is also a Morley sequence in the sense of non-forking.
Itay?
Yeah.
Is it equivalent to simplicity? Dividing equals Kim dividing?
No.
No.
This is also true in other models. No, this is also true.
No, over anything.
I mean, I just defined it over models. So
okay.
Over anything, you have to think. Yeah. Okay. So because otherwise there might not be such types.
Okay.
Right. This is true in TP2 as well. Okay. Anyway, a lemma is right. This is the lemma I want, that Kim's lemma for Kim dividing. Okay. But it's not really Kim's. Yeah. Okay, we had the discussion, but still, it's a nice name. So suppose phi of xa Kim divides over some model M. I'm assuming here NSP1. Okay, suppose then, and Q is a global M invariant type. Q extends the type of A over M, Q of Y. And I, as before, realizes Q. Then phi of x AI is inconsistent. Okay, so it says if you know it Kim divides, by knowing that it Kim divides, you only know there exists some such sequence. So this says for all such sequences. Okay, exactly answering Anand's question. Okay. Okay, so the proof is really easy. I hope I won't mess it up. So proof. So suppose, because it kin divides, there exists some R witnessing it, since phi of xa kin divides, there exists some R, some global type, and invariant witnessing this. So it's something small that I didn't say, but here the I, once the only thing that matters is Q here in this definition. If I change I to some I prime realizing Q, so it will have the same type. Q to the omega restricted to M is a complete type. So what's really important here is the Q. So suppose there is some R, some global invariant type which witnesses the dividing. Okay, so now what we're going to do is we're going to look at the following thing. We're going to define A0. It's going to be a bit funny. So A0 realizes, so we have Q and we have R, right? So A0 realizes R restricted to M, okay? And B0 realizes Q restricted to M A0, okay? I'm just constructing a sequence. So now A1 we realize, okay, before I continue, let's just see what we have on just A0 and B0. We have that A0 and B0 are the same type of M. Because, right, because, yeah, because both R and Q contain the type of A over M. Okay, they both contain this type. So A0 has the same type as B0, which has the same type as A. Okay. Okay. Now let's move on. So A1, as I said, A1 realizes R restricted to M A0 B0, and B1 Q M A0 B0 B1. Actually, I don't think I need B1.
A1.
Yeah, I'm not sure I need A1 here. Okay, so again, we have that A1 has the same type as B1 over M, right? But they definitely have the same type over M, right? A1 and B1, because still they satisfy Q. But yeah, wait, and A0, yeah, A0 have the same type as B0. So I want to say now that A1
why should R restricted to A0 B0 the same as Q restricted to A0?
What? Oh, I'm just saying over M they're the same type.
No, but then you want to conclude that over A0 B0.
No, I don't think I want to conclude that. I think what I want to conclude is that A0 B0 they have the same type over M A1 B1.
Going backwards.
Yeah, I'm going backwards. I think I want to prove that.
Going backwards to Christmas. No?
Yeah. What?
Backwards to Christmas.
Yes. So yeah, why is this true? Because right, because A0 and B0 are the same. So what we have really is we have that A1, B1, they are invariant. So let me just write I here. So they satisfy R tensor Q over M A0 B0, right? And A0 B0 have the same type over M. A1, oh yeah, you're right. So it should be Q, I think it should be Q tensor R, right? That's okay now? What? And B1, A1? Yeah. Yeah, okay, right. Yes. Thank you. Okay, so A0 and B0 are the same type over M. but then they have to have the same type over A1, B1 by invariance, just by invariance, because this type, this is an invariant type. Okay, this guy is an invariant type. So with whichever formula, so this is something in general, like if C realizes Q over M EF and E and F have the same type over M, then E and F have the same type over MC. Because any formula that holds for C with E, it will also, I mean, that means if phi of E and C holds, then phi of XC belongs to Q. So phi of XD belongs to Q. So phi of, wait, there was no C. Wait, what do I say? EC, sorry. This is supposed to be X, and that's supposed to be E. And yeah, there was no D. So this is supposed to be X, and that's supposed to be F. So phi of X. Okay? Right? I don't think I'm okay. So yeah, whatever formula C holds with E, it also holds with F. So we have that E and F at the same type of length. Okay, this is kind of cool. The thing that we know now that A0 and B0 have the same type of M, so they also have the same type of A1, B1. Okay. Okay, so now this was the main thing. Okay, so let's continue. Now we have, in general, let's say we continue. We construct A. So which order did I do it in? So A n plus 1 realizes R restricted to M A less than N, B less or equal than N, and B n plus 1 realizes Q restricted to N, B less or equal than N, and N plus 1. Okay. So, and then again, I have that A0 at the same type as B0 over M and all the other guys above it. A1 is the same type as B1 over M and A bigger than 1. And so on. Okay? Exactly the same reason. Exactly the same reason. Okay? You can prove it by induction. Okay, but then now we see that now we get a finite sequence, right? So this goes all the way to AN plus 1 at the same type as BN plus 1. So it goes backwards, right? It goes backwards, but it's important. So now the first column satisfies R, I hope, and the second column satisfies Q. So this is a column in R to the N plus 1, and this is a realization of Q to the N plus 1. Okay, so by assumption, this thing. So anyway, so if I by compactness, we can find AI BI such that AI is satisfies R to the omega, BI satisfies Q to the omega, and AI has the same type as BI over M A left. Okay, so now I do it. I wrote it in the right way, and this was backwards, but now I wrote it forward. Okay, I can do it by maybe not omega. It's the omega star. Okay. Anyway, yeah. I mean, the thing is that here the A1 satisfies R over A0, and here really, I mean, no, it's not any.
At this point, it's just bookkeeping.
Yeah. It's like, but
you made the argument.
Yeah, I did. I made the argument, and now, yeah, by compactness, I have this. Yeah, going backwards. So, yeah, if you want, maybe make it for the type Z, okay, to make it absolutely true. Okay, and then we write A bigger than I, B bigger than I. Okay, so make it all the type Z, and then we reverse the order, and we get that one column is K consistent, K inconsistent, because this is a column of R. So the second column also has to be K prime inconsistent or some other K prime, which will give the, okay. So it has to be inconsistent in particular. Yeah, I'm exactly using this fact. Yeah, we get two columns, right? And after I do this, I reverse the order. Okay, I reverse the order, and then I get two columns which exactly satisfy the first part. So and I satisfied 1 and 3, so that also cannot satisfy 2. Okay, so the second column will also be K prime inconsistent for some K prime, and this will give the proof. So I'm not writing all the details. It's I think it's pretty clear now. Okay. Okay, it's exactly. So now conclude by the lemma we proved last time by previous. Okay. Great. So this is really the starting point of. So once we have this Kim's lemma, we can define forking right now. And okay, so let's define forking. Okay, so definition. So phi of XA Kim fork over M if there exists some psi 0 of XA0 psi K and let's say psi N of XAN minus 1 such that psi I of XAI can divide over M for I and phi of XA implies that disjunction. Okay, so it's the usual definition of forking. It's the usual definition, but with this dividing instead. And now right, and so you can define a type. So P of X, any type now, like let's say a global type or whatever, S of B for B containing M, does not or forks over M if it contains Kim forks. I'm sorry, Kim forks. If it contains a Kim forking formula. So it's a usual definition, okay? And then just by the definition, without even knowing what it means, you know that if P you have a type, yeah, if P, so it's easy that if P belongs to S of P, P contains M, does not Kim fork. So I'm going to write DNKF. Okay, so K should be capital.
K is for Kim.
K for Kim.
By the way, whenever you use the word Kim, it's like a mention of Kim or just a technical thing.
Is it both? Could it be both?
Because like people say, how many mentions you get? A lot of mentions.
Yeah, so for you it would be a technical, okay? I don't mind mentioning him. So so yeah, if P doesn't fork and C contains B, then P has an extension Q. So that Q also. Okay, so this is just by the definition completely. It's a formal thing. Okay, it doesn't use anything about this specific definition. Just because forking is an ideal, really it uses the fact that forking is an ideal. Okay, nothing. But now by Kim's lemma, corollary of Kim's lemma for Kim dividing, yeah, is that Kim forking equals Kim divided. So a formula phi of xa Kim Fox over n if and only if phi of xa Kim divided. Okay. Okay, so this is pretty. This is also true in the simple case. Or this is parallel to what's going on in the simple theories case. Well, in simple theory, the formula forks if and only if it divides. So and with the same proof, and here we just add Kim everywhere. Yeah. So this is like a pigeonhole thing. So suppose let's say so proof. Let's say that n there is 2. It's enough to prove it for n equals 2. Okay, you do it by induction. So let's say that n is 2 there. So phi of xa implies psi 0 of x a0 or psi 1 of x a1. So now let q of yz be, so this is be a global cohere such that q contains the type of a0 b0 over n. Okay, and then no, let's add a w here and contains the type of a0 b0 a. Okay, so let's say w. Okay, and then we'll see that so let now I have to, okay, so ci di fi realize q to the omega, and then we have that phi of x fi implies psi 0 x ci or psi 1 of x di, right? Okay, and we want to show this guy is inconsistent, right? Now we know. So suppose if C thinks C is okay, no, C is not okay. E realizes phi of x fi or I, then for infinitely many, then there exists some infinite set for, yeah, so for some s subset of omega infinite, we may assume that, I mean, either for C or for the D, we assume that E satisfies psi 0 of x minus, or replace O for and DI. So either for Ci or for Di, it satisfies an infinite set, but that's obviously a contradiction, right? Because they both are inconsistent. Okay, so
Because
That you can choose any, yeah.
because, yeah, of course, yeah, exactly because of Kim's theorem. Because we know that this is inconsistent. This guy is inconsistent by Kim's. Okay. Yes. Okay. So so this gives you that Kim non-forking equals Kim forking equals Kim dividing. Yeah, exactly the same proof. Exactly the same proof. Yeah. Because in simple, yeah, it's exactly the same. So what we use here really is the existence of universal witnesses for dividing that you can find easily a witness for dividing by taking a Morley sequence in the type of the parameters. Right. Okay. So a corollary of Kim, another corollary of Kim's lemma is what they call weak symmetry. So another corollary. So again, I'm assuming n is P1. I'm always assuming. Then if B, let's see. So let's say that this means, this I here means there exists some global invariant type Q extending type of B over N. This is the I here, okay? I stands for invariance.
So M invariant?
Yeah, M invariant. Thank you. So this implies a. So let's call this one. This is weak symmetry. This is weak. Okay. Okay. So this is very similar to how you prove symmetry in simple theories, really. And so what you do is, because you know this, you can realize the proof is, take this Q. So let Bi realize Q to the omega over Na. You can do it such that P0 equals B. Okay. So this will be an indiscernible sequence. So it's I. So I is indiscernible over Ma. And it's of course a Morley sequence in some invariant type. So this follows now. Okay. Because if some formula here Kim divides, then this sequence will witness it. But it's indiscernible over A. So it's impossible. Okay. Is that okay? I did it a bit fast, but
Can you say that again?
yeah. So so I is indiscernible over Ma. You agree with this, right?
Yeah.
On the other hand, if phi of x b Kim divides, phi of xb belongs to the type of A over MB, yeah, then phi of xbi is inconsistent because of Kim's lemma. Kim's lemma said any, but A realizes this because it's indiscernible over A. Okay, so this is how we get this weak kind of symmetry. Okay, so we started with something way stronger than Kim, and we got. I mean, on his face, it looks stronger. Okay, I mean, it is stronger. It's not stronger. Okay. So let me just give quickly some example, just to so that you feel what's going on here. Okay. I hope that I'll do it correctly. So the example is the selector function. So the language has two things. It has two predicates O and F and E. So these are disjoint predicates. I mean, I'm also stating what the theory is. E is an equivalence relation on O. And okay, so far, and we have O, which is we think of as object, is an equivalence relation on a set of objects, and F, I want to think of F as functions. So we also have a function Eval, where Eval is a function from F times O to O. Okay, and this Eval should be a selector function for the equivalence relation. So Eval of FA is always equivalent to A. I'm saying what the axioms are here. Okay, and what is the other part? That if so I'm thinking of this thing as f of a, eval of f of a is f of a really. So yeah, if a is equivalent to b, then eval of fa equals eval. Okay. So it chooses an element. So it's like it selects. So it selects an element from each equivalence class on the one hand, and it's unique. So if A and B are equivalent, then it selects the same element.
What is the difference between the different F in that?
What? So, sorry, what's the question, Bobby?
Why do you have many Fs in F?
Why not?
When you say you're requiring that they're different? Or
No. Okay, so this is so far these axioms that I kind of wrote down. These are universal axioms. Okay. These are universal axioms, and now this theory has this set of universal axioms has a model completion. It has amalgamation. It's of a set class, and it has a model completion in which it has quantifier elimination, and we'll call this one T. Let's call it a selector function, okay, SF. So this is the model completion. So this is this example is very similar to, it's a variant of an example Shelach introduced called the TFEQ. TFEQ is a parameterized equivalence relations. It's very similar, but here we have a selector function. So anyway, TSF is NSOP1, and I'm not going to prove that. Okay, yeah, it's possible to prove using this characterization using this kind of Kim Pillai style characterization of existence of an independence relation.
As is TFEQ.
What? Yeah,
As is TFEQ.
both of them are. Yeah, both of them are NSOP1. Yeah. Yeah, but anyway, so let's look at the formula. So now let's take a model M.
But this is not simple, right?
What?
This is not simple.
Yeah, it's not, and I'm going to show you
Okay.
very soon why it's not simple. Okay, even though it's not difficult to show, it's not simple directly, but by actually showing it as TP2. But anyway, let me give another proof. So M is a model, and let's look at the formula. Let's take A such that A, the equivalence class of A is not equivalent to anything in the model. Okay. So like this is the model, it has classes, and A is here, and the class of A is also, okay? This is possible. And now we look at the formula eval of, so let's call it X, eval of XA equals A. So this is a formula phi of X. Okay. Okay, so this formula, so phi of XA, it divides, but not King divides. Okay, it divides because if I go over A's in the same class, if I take A's in the same class, I can't find any function which gives all of them the same guy, the same element, because it's a selector function. It should choose because of this. It should choose for every class just one representative. So it divides because I can choose A's from the same class, but it doesn't Kim divide because any invariant sequence starting with A will have will be in different classes, and then I can choose some F that chooses for each one of these representatives.
So again, this formula divides.
It divides.
By letting A range over the class of A.
Yeah, by taking AI, because I can take AI, and all of them are equivalent to A. Okay, and then this is a witness of dividing. I cannot find any function, any selector, which will choose for all of them the same guy.
Doesn't Kim divide
Because if it so F, yeah, it can't be that F eval of F. Yeah, maybe it can be that F of F eval of equals both A0 and eval of FA1 equals A1. I can't, because I mean, assuming they're different, assuming they're distinct, they're not the same guy, right? So f of A0 must be equal. We know that they have to be equal.
If what?
If they're all equivalent.
Yeah, but if they're not, but you're not taking the AI different.
They're different, but still equivalent.
So to show it doesn't kin divide.
Yeah. Sorry. I thought we were still here.
No.
Okay. Yeah. To show them that it doesn't kin divide. Okay. So take now AI, a sequence satisfying some global finitely satisfiable type. Yeah. If so, Y doesn't kin divide if Q contains the type of A over M and finitely satisfiable in M. So Q is a global type. Then and AI satisfies Q to the omega. Then AI is not equivalent to AJ. Yeah. Okay. Because if it was equivalent, then there would be some guy in M which is equivalent to it, but we know that there's nobody in it. And then we could choose, and then we can choose F such that FAI equals AI. We can just choose these ones to be the representatives. And okay, there's something to show that really by the model companion you can find it in actually in a model. Really. Okay, but the fact. So okay, and so kin dividing is not the same as dividing, and I already said that in simple theories it is the same. So this shows that it's not simple. Okay. And actually, it's even worse because if you look at the formula, eval of XA equals A, or X, or Y is equivalent to A. So this would be a formula in two variables over A. This formula forks, but doesn't divide. Essentially because of the same reason. If you take any indiscernible, suppose it forks because both of those divide, but they divide for different reasons. This divides because it kin divides. Sorry, this divides because it divides. It doesn't kin divide, but this one does kin divide because A's are different classes. And then you can show it doesn't divide because if you take any indiscernible sequence starting with A, either it is in the same class or it's in different class. And if it's in the same class, you can do this, and if it's a different class, you can do this. So it doesn't. Yeah, I know. You want to take a break? Okay, so yeah, let's good. So let's take a 5-minute break, and then I'll start with symmetry. Yeah.
Is it on?
Yes.
Yes.
Okay.
Yeah. Yeah. רגע, האמת שבסדר גמור, ממש. כי זה מאוד מפתיע, ברגע שיש לך את המערך הזה,
כן, הכל נהיה יותר פשוט.
כאילו ההוכחות האלה פשוט ידועות, פשוט לעקוב אחרי ההודעה שלך, איך זה
כן, כן, המערך הזה היה הדבר העיקרי, ולא הבנתי את זה, כאילו, אוקיי, נכון שיש לו קצת קשים בהמשך?
לא,
כאילו, אני לא עשינו עכשיו את זה.
Yeah, so okay, so can I
Yeah.
Just an announcement for that this course today is Itay's, this is his last talk, and the next two. So Gabe, what happened? I want to announce that you're speaking.
Next week, that's okay. The week after, we decided.
Okay, so in principle, this course finishes on November the 30th, which is a Tuesday, 2 weeks' time. Is that right? Yeah. And the idea is that Gabe Conant will be talking about continuing this course of stability and combinatorics, roughly. But next week, so next week it'll be Gabe will talk. It'll be announced. Who does the announcement? Miriam does the announcements, or who puts this, anyway? You know, I mean, announcement. I mean, in the on the website. Okay, someone puts it so on the website. So next week will be the same time, 11 o'clock. The week after, there's a combinatorics workshop, and we're not completely sure of the timing of that and how the timing of that will fit with the timing of this. So the last talk, we have to decide on the timing in 2 weeks' time. Okay, thank you.
Can you, everything is okay. I turned on the microphone right and now, so, okay. Anyway, yeah, now I want to go to actual symmetry. So here's a statement. So the theorem is under NSFP1, if A is independent from B, then B is independent from A. Actually, it's equivalent to NSP1, but I'm not going to prove that. Also, Kim's lemma for Kim dividing is equivalent to NSP1. A lot of stuff are equivalent to NSP1. And also, yeah, I forgot to say that the last thing I showed was an example of a formula which forks but doesn't divide. But that's not a contradiction to the previous thing, because before it was with Kim forks and Kim divide. Okay, so that's a big distinction. So forking is not the same as Kim forking. Okay. Okay, so the proof I'm going to give of this theorem is a variant of the proof that we gave in our paper. It's by Jan Dobrovolsky, and he simplified our proof in many ways because, for example, in our proof we needed to construct some kind of infinite tree, and he was able to do it with finite trees. So that's one thing, and also he was able to remove lots of the indeterminability stuff. So it really is a simplified proof, but it has the same idea. So it shows the idea, but not, it removes all the technical indiscernibility stuff. So let me start, and I'll see if I manage to do it. Okay, so let E of x, so this is A over M. Yeah, that's be a global core. Okay, so we are going to fix. Okay, we're going to fix this P all the time. So assume it's not the negation. Assume the negation. So B does scheme for the type of it does scheme for. So there is some formula phi of YA phi of YA in the type of B over MA, which Kim divides. I forgot to say that I forgot to introduce this notation. Sorry, nobody asked, but this notation just means the type of A over BM doesn't kinfolk. Okay, it's the usual notation. Nobody asked though. So okay, so if not, then there is some formula which witnesses that the Kim dividing. Okay. Now by Kim's lemma, can I write here? I guess not, right? So by Kim's lemma, and there exists some K such that if AI satisfies P to the omega, remember P is this global coil which we fixed. Then phi of YA is K inconsistent. Okay, so there is some K like this because because Kim's lemma says that any sequence, any coil sequence will witness dividing. So in particular, a sequence in P. Okay, so what we're going to do is to contradict. We will build to contradict n sub p1. We will find for each n, for each number n, di I less than n and ai I less than n, such that di is the same type as ai over previous things, and phi of y di is consistent, and phi of y ai is k inconsistent. What?
AI already satisfying
But that was quantified, so that was if here. You're right. So let's, instead of AI, let's going to mess up things later. But okay, no, let's call these ones agi. Okay. I think I probably will use age at some point, but you'll forget. So okay. So what we will find is for each n, I'm going to construct sequences of length n, such that the left column will be consistent, and the right column will be k inconsistent for this specific k. Okay. Actually, the AIs will satisfy. They will satisfy p to the n. Actually, in the end, they will satisfy. That would be the reason why we'll get inconsistency. Okay. Okay. So how do we do that? Okay. So let mu be 2 to the t. Okay. So the only cardinal is going to appear here. Okay, 2 to the t plus. Yes. Okay, now we construct a sequence CS S in mu to the less than n, and es in where s is mu to the n minus 1. So here I'm assuming, yeah. So I'm fixing, let's fix n at least one. Okay. So I'm constructing a tree. The tree will be, there will be the nodes will be CS, but there will also be BS, which are only the leaves. Okay, the BS are only, maybe I'll call it T, just not to confuse. So the BTs are only for the leaves of the tree, not the nodes. Okay, such that yes. So first, if T is in mu to the n minus 1, so T is a leaf, okay, a leaf in the tree, and S is somewhere below T. It could be equal to T, but could be also below. So if then the type of CSBT over M, maybe I'll write it like this. Then BSCT has the same type over M as BA. It's the original BA that we had in the beginning.
And maybe.
Oh.
Yeah.
CSBT as AB. Yeah, sorry. I switched the. Okay. So I'll do a drawing after I finish writing the conditions. Okay, so this is condition 1. Condition 2. Okay, maybe I'll do a drawing at the same time. So the drawing is the tree is going to be really, really wide. It's going to be really wide. This is mu. And okay. And so let's say here in every node I have some C, but in the last nodes I also have some Bs. Okay, so the Bs also only live in the leaves, and the condition is that if I take yeah, if I look at for example DC and this B, they will have, so this C and this B, they will have the same type as AB. And okay, so this is the first condition. Second condition is if S for S in U no, so N such that it's what I wrote was okay. So if S is such that its successor, like the length plus 1, is also less than N, then for any S like this and alpha less than mu, we have two ordinals, beta less than alpha less than mu. The condition is that C, S, and then alpha realizes P. P is this, remember, P is this global coil we chose. M, P restricted to M union and CT S. Okay, so C alpha realizes P restricted to M union. So I'm going to draw it here. So the second condition is, so the second condition says that this guy realizes P restricted to everything here. Okay, that's the second condition. So I'll say it again. So this guy, this is C, let's say this is C, this is C, yeah, so this is C alpha, this guy. And here we have this guy, which is C, this guy, which is C beta I don't know, gamma, whatever, this is beta here, this is gamma, then the condition is that C alpha satisfies P, which if it's in particular C beta. Okay, so going on the right in the tree, these guys satisfy P with equal to everything on the left. Okay, that's the condition. Number 3, the final condition is that the root, this is the root of the tree is scheme independent from everything above it, and also all the beads. That means bigger in the tree order. Okay, that's the empty set. Yeah. That's the root of the tree. Yeah. And that means bigger in the tree order. So that means everything above the empty set. So everything else, just scheme independent from everything else. So this statement, this drawing became really messy. So this statement says that the root, which is this guy, is independent from everything else. Okay, including the bees. Okay. 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 Now I hope this will be enough to prove this. So suppose I did it, and now I want to show how to construct this. Okay. 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 So why helps? Why it is enough? So first, I want to construct this. So let D0 equals A0 be just the root. Okay. And I think that I'm going to draw it again. Okay, here, so that it will be clear what the choice is. So here is the empty set. Here is the C. Like, let's say this is C0, this is C1, and in general this is C alpha, and here we have C00 and C0 alpha here. Okay, and on the top we also have the B's. Okay, so suppose the tree has only two levels, and we also have B00. Okay, B0. And again, the condition is that the pair, this guy and this guy, has the same type as AB. This guy is scheme independent over everything above it, and this guy is satisfied P over everything to the left. Okay, so first I'm choosing D0, A0 being the same guy, and now I want to choose D1 and A1. So they have to satisfy, D1 and A1 should satisfy that they are the same type over the root, C empty set, right? Now, and just look at the first level. Okay, I can find two alphas and beta. So find alpha less than beta, no, beta less than alpha. Sorry, I want to be the same notation such that C alpha and C beta have the same type over D0 and D and A0, which is just C empty set. I can find such things because it's pretty big. I mean, I'm just looking at the first guys. Okay, so of the first guys, this is by pigeonhole. Okay, just by pigeonhole, this is big. So there are two guys which have the same type over this. Okay. Okay. And now after I did this, let me choose the next one. And so the next one. So okay, so let let that D1 be C beta, and A1 be C alpha. Okay, so let me in the drawing, it looks like this. So this is C beta, and this is C alpha. So this guy is, I'll take another color. This guy is, this is D0, and this is this is D1, and this is A1. Okay, and this is D0. Okay. So how to continue? to continue, I'll just look at these guys, starting from C beta. Okay. So then I can find, again, I can find C beta, I don't know, C beta gamma, which have the same type as C beta delta. Let's say delta is bigger than gamma over everything before. So A0, AI, or the A less than 2, B less than 2. And they're both starting with beta. Okay, so now I'm looking at this. So yeah.
All these little subscripts become the positives of the root.
Yeah.
It's very, very small.
Yeah, so this is why I'm drawing it. Okay. So forget about the subscript. Just follow the drawing, okay?
I don't want to follow the drawing.
Oh, don't follow the drawing. Okay. So let me write it again, okay?
Just maybe use the other board or something.
Yeah, I'll use the top board, okay? This part, okay? So far we have D0 equals A0, which is just the root. And we have D1 is, D1 is C beta. And A1 is C alpha. Alpha is bigger than beta. Okay, so that they will have the same type over this time. And then D2 will be C beta, C beta gamma, and A2 will be C beta delta, where delta is bigger than that. And that's all. I'm not going to continue. It's obvious now how to continue. I just want the things to have the same type. Okay, I did it for 3 guys, so it's enough. Now, what I want you to notice is that these guys, so okay, write it in this board now. So if I look at the D's, you can still see the D's, right? So then I'm using the same notation. So B beta delta, beta gamma, sorry, B beta gamma satisfies phi of y y d0, phi of y d1, and phi of y d2, right? Because this is because of condition number 1. By condition 1. Okay, because the left guy, the B's that we put there, they satisfy P even, the whole type. So definitely phi. Because all of those, they came from the same branch. D0, D1, and D2, they came from the same branch. D0 was the root, D1 was beta, and D2 was beta gamma, yes. So it's the same branch, and beta gamma is the leaf of that branch. So it satisfies all of it. So condition 1 gives you consistency, right? Now we also have that A1 satisfies P. Oh, wait. Wait, I might have made a mistake here. But what we do know is that we do know that A1 satisfies P restricted to A2. Yeah, I think I messed some stuff up, but it doesn't matter. So we do know that A1 satisfies P restricted to A2 because A1 is where did I choose A1? Yeah, A1 is C alpha. So C alpha satisfies P restricted to C right? That's exactly condition number 2 here. This is S. The S here is I'm just applying this by condition 2. Right? Because I'm applying this with S being the root, and I get the C alpha satisfy this. Okay. Okay. Yeah. So I should start here not from 0 but from 1. Yeah. Forget about the 0 1. So yeah, I don't know that A1 satisfies P restricted to A0. This I don't get, but I do get that A1 satisfies P restricted to A2. So this way I built I built the D1 A1 and D2 A2, and A2 satisfies P restricted to A1, and D2 and D1 are consistent. And this way I can continue. Okay, I just can continue. Now I'm going over this branch. I'm choosing some guy above that, two guys above that, which have the same type, and I'll get it. Yeah, and I'll get now that A2 satisfies P restricted to A2, A3, and A2 satisfies P restricted to A3, and so on.
But why did you use condition 3?
Yeah, I didn't. Condition 3 is for the construction. Oh, I didn't even. I erased it.
No, it's on the right, top right.
Top right.
Top right. Oh, yeah, yeah. Thank you. Okay, yeah. So no, condition 3 is for the construction. So I just wanted to. So is this okay? This shows why it's enough. I illustrated it. Again, what?
What about condition 3?
Yeah, yeah. This is for the construction. Here I explained why it's enough. But to construct it, I need to.
It's part of the inductive construction.
Yeah. For the construction, I will need condition 3. But for the conclusion, I don't need condition 3. I can forget about it now. Okay. So really, that's okay. That's the idea of why it's enough. So let me go to the construction. Do you have any questions? Why it's enough? Is it clear? How to continue? So continuing, yeah, you just choose two guys having the same type, and they will satisfy P, and so on. Everything will be fine. Okay. Okay, the construction is also not difficult. So
I mean, you use compactness, right? I mean, for every n you have different.
Yeah, of course. Yeah. For what?
I mean,
for every n, we
you have
find
different elements, no?
But yeah, but it's the same k. That's the important thing. It's the same k for the k inconsistency. It's the same k.
Yeah, of course.
So we can use compactness.
Yes, that's what I'm saying.
Yeah. Right. In the end, use compactness. And okay. So now the construction. So let's start. So I need to begin. So the beginning would be n equals 1, right? Okay, for n equals 1, I can just choose the root to be a, and yeah, actually the tree is just a root in this case. For n equals 1, so the tree is just a root, and b will just be b, and yeah, that's it. Yeah, and then I have exactly what. Oh, wait. Here it should be for the case of the B in general would not make sense for the root, but okay, but in this specific case it does. Okay, so I have it, right? I have condition 3 in this case. Okay, so it satisfies that it came independent, right? N over n, and the type of AB is the type of AB. So there's nothing to check. Okay, and so let me show you how to do the next step, and hopefully this will convince you that you can do it in general. Okay, so you look at right. Okay, so let's take the type of A over MB, and let's choose some Q of X and Q global type, which doesn't kinfolk over M. So here I'm using just the fact that A doesn't fork over B. So I can find some such thing. Okay. And then let E realize Q restricted to A.
It doesn't mean invariant, right?
No, of course not. No. This is weaker than invariance. Yeah. So just a global type, it doesn't kinfolk over M, and I take some realization of that type, E. Okay. Right. Okay. Yeah. Now, yeah, you have like 10 minutes. So I'm going to use two things which I didn't prove really, but okay, I'll say them when I get to them. Okay, so I take this E, and now I have that E as a king fork over M from A, right? And the type of EB is the same type as AB, right? And the type and EB the same type as EA. So this I can do. Okay. Okay. And now what I want to do is to what does this sound? Okay. Now I want to look at the type. What? Yeah. Okay. So what I want to do is to look at the type. Let's say that R of xy. Yeah, xy. Yeah, is yeah equals the type of AB over M. Okay. And then I claim that P of X, remember P is this global invariant type. P is this global invariant type. Union R of XY extends to a global cohere. I need another name, so let's call it Q of XY. Okay. Over M. So this is finitely satisfiable. It's a global type. This guy is a global type. Finitely satisfiable in M. This one is not a global type. This is a type over M. But I'm saying the union extends to a global coil. So this is an exercise really. Okay. So don't call it Q. Let's call it V. No. Okay. I don't know. What other types are there? What other? S?
No, but you
No.
have S.
Let's call it Q bar. Okay. I'll just call it Q bar for this. You can forget about it soon. Anyway, so I have this Q bar, and this claim is just this is really an exercise, but it's really an easy exercise, not like a one Sylvan view. So this is like immediate from the definitions. Okay. So yeah, just immediately from the definition. This is finitely satisfiable, so it extends to a global. This is really easy. Okay. So that's the first thing I need to do. I need to this claim. Can I write this? Yes. Okay. So now let me so this type is in AB. So let AI BI I less than mu realize Q bar or to the mu over. Okay, so you have this AI. Okay, this is an indeterminable sequence over M. The second part of the claim that I need, second claim that I need is that for the claim, I have some more notations. I have Q bar, so now I need another type. Really, Q prime. Okay, Q prime is the type of EAB. Okay. So this is Q prime of X prime Y. Okay. So this is a type of E over ABM or EAB over M. And then the claim is that the union I less than mu of Q of X AIBI, this is a partial type. This is a partial type. Q prime. Yeah, this is a partial type. Doesn't king fork over. This is the second claim. Okay, this is a slightly more difficult exercise, but it's also so this follows this is just a general, now it's a general thing because I know, so this follows from the fact that E doesn't kinfolk with AB. And so it's now a general statement and Kim's lemma. So maybe I'll just explain how to do it in words. So take this AIBI, and then take this. You can, by Ramsey compactness, assume that this sequence is indiscernible over E, but then it will follow. It will automatically follow that this type doesn't kinfolk, just because any Morley sequence, if you look at n tuples of the Morley sequence, it will still be a Morley sequence. That's essentially the proof. That if you look at n tuples of Morley sequence, it will still be a Morley sequence. But I didn't give the whole proof. Okay, and now this is more or less it, because now we just define the tree, the next guy. So we let C C the root, the new root will be just a realization of Q prime of the union. Let's call this Q double prime. What? No, we constructed the tree.
What?
No, before we said there is going to be a tree, and now I'm going to construct a tree. Oh yeah, so the new C root.
This is n equals 1.
Yeah, this was for n equals 1. Now we're in n equals 2. So now we're in sorry. So yeah, we're doing it by induction. Yeah, so now we're in n equals 2.
But this is
For n equals 2. Okay, so for the construction for n equals 2, so we start with C, the root, the new root will be just a realization of Q double prime. Okay, and C alpha will just be A alpha. This is Q double prime.
Sorry.
Yeah, Q double prime is just this guy. C alpha will just be these guys, A alpha, and B alpha will just be B alpha. And now, yeah, and now you can just continue like this. Okay, every time you, so one. Okay, so that's I'm doing it a bit fast because not time.
Level 1 stuff.
Yeah, this is just level 1. Now we have like we constructed this. That's level 1. Okay, we just constructed the first level, and now how to continue. So now we have we constructed so far. We are very happy. The construction just continues exactly the same way. We are very happy. We are in this case, and now okay. Let's see. So this is the drawing that we have. This is the root, C empty set. And now we continue the same way. We find this again, exactly the same way. We find this new E, which will be like I imagine it below what we constructed so far, but independent from all of this, and still satisfies everything that it should satisfy. And then we take copies of this, such that this guy will satisfy P over the previous guys. So exactly using this first claim that I had, this claim. Okay. So I'm taking copies such that this guy will satisfy P over the previous guys. And then again, I know this whole union is doesn't kinfolk, so I can find some E prime that it satisfies. Okay, and then this will be the new root. This will be the first, and then the second, and that's it. That's a proof. And then I can do the second step. Okay, yeah. So this is a symmetry. Yeah. Yeah, exactly for this, exactly for all of this stuff, to show that something, that I can find something satisfying something. I need, how else do I find this E double prime P? Yeah, is to find the new roots. Every time I need, exactly the non-forking gives me this. So you see, this is kind of an independence thing going on, somehow kind of amalgamation thing going on that you, yeah, so I'm out of time, so I'm going to finish, but I just want to say that so this proof is really nice because it doesn't have anything infinite except this mu. The trees are very wide, but they're not high. They're very shallow trees. Okay, they're finite trees. But our original proof was with infinite trees, and then we found kind of indiscernibles. And actually, maybe our approach is better to think about these things because to prove something like the independence theorem, I think it is more natural. Our proofs are probably more natural, but the independence theorem is a bit more complicated than symmetry. And later, there's also other results like transitivity and yes, and local character. And in fact, maybe I just say the last thing we know. This is really some fact that in the end we know that finally we know that phi of xa Kim divides over n if and only if for any Morley sequence in Kim, in the sense of Kim non-forking, let's say AI, we know that this guy is inconsistent. So the beginning of the story was that we defined Kim dividing in the sense that of Morley sequences in coils or in invariant types. But actually, after all the stuff, we know that it's the same as saying that any Morley sequence in this notion will show will be inconsistent. So we go back to it's exactly the same situation as in simple theories. This is the same situation as in simple theories, but we somehow need all this stuff to get there, which is a bit funny. Maybe there are easier proofs to do it. And of course, once you know that, you can easily get symmetry. Then symmetry will be almost immediate with just the same proof as the proof of simple theory which I showed you. Okay, so I'll finish here. Okay, thank you.
Are there any more questions?
Yeah, I've got no questions, but just want to say thank you very much for Itay for this. Was it you gave 3 lectures altogether? Yeah, for 3 lectures on as part of this course. And do I have actually a question? I mean, what about all the applications of the machinery? This application of the machinery somehow, in some sense, applications of all this machinery about NSOP1 theories. I don't know what I mean. I don't know what I mean. I mean, I'm not sure what I mean, but just.
Actually, I don't think it's like simple theories. Once you have all this machinery of simple theories, you can use it to analyze specific examples, like ACFA or something. I don't think we've reached that stage.
Okay. But anyway, thank you very much to Itay Kaplan for this. And just to